Large-scale desert restoration is typically reserved for trillion-dollar geoengineering projects. However, a $9 bioreactor demonstrates that we can synthesize fertile soil on a localized level using basic chemistry and desert sand. The engine driving this process is a mycelial membrane. Instead of using fungi solely to decompose dead wood, we are deploying them as living bioreactors designed to physically digest inert sand. By injecting low-cost chemical precursors into a highly pressurized vessel, we trigger a specific metabolic reaction. The intense pressure drives the mycelium to break down sterile mineral particles and synthesize life-sustaining soil. We no longer need to rely on massive industrial supply chains to restore dying ecosystems. By combining these precursors with atmospheric pressure, we can engineer fertile loam directly from the sand grains themselves. Look at the 2026 expansion of the Sahara. Traditional reforestation projects across this boundary have flatlined because planting trees in dead dust inevitably fails when the climate turns hostile. If you truck in standard organic compost, it breaks down almost immediately. At 50 degrees Celsius, the extreme heat triggers rapid oxidation, baking the organic matter away before roots can establish a foothold. Because it oxidizes so quickly, that standard compost loses its cellular structure. It hits a point of zero moisture retention, leaving any added water to evaporate right back into the atmosphere. Agricultural methods designed for temperate zones collapse here. To survive this atmosphere, the biology requires an entirely new cradle, an artificially pressurized shield to block out the heat and trap the moisture. Methodical, step one is building that shield. The entire bioreactor requires only two core components: thick recycled polymer sheets and a basic mechanical pressure valve. We cut the recycled polymers into geometric panels and fuse the edges together to form a rigid enclosed hull. This specific shape yields the maximum internal volume while minimizing the surface area exposed to the direct sun. Next, we coat the exterior with a dense layer of mechanical grit. This grit acts as a thermal buffer against drastic temperature swings and protects the underlying polymer from constant sand abrasion. Finally, we install the pressure valve at the top. Once sealed, this valve completely locks out the harsh external environment, allowing us to dictate the exact atmospheric conditions inside the hull. This $9 hardware shell provides the physical armor required to keep fragile biological processes alive while buried in a scorching desert. Inside the reactor, we introduce a specific strain of bioengineered mycelium. We selected this fungi specifically because it thrives under immense atmospheric pressure. Through the valve, we inject a concentrated liquid mix of low-cost nutrient precursors directly into the sterile desert sand we have packed inside. Under these high-pressure conditions, the mycelium's metabolic rate accelerates. The white fungal threads weave aggressively through the packed sand, physically cracking open the raw silica to extract trace minerals. This chart tracks internal chemistry. Notice the carbon dioxide line dropping sharply as fungi lock atmospheric CO2 into a solid biological matrix. The timeline shifts here, displaying a steep rise in nitrogen and moisture capacity, confirming it's now nutrient-dense loam. The physical seal dictates the reaction. The artificial pressure serves as the literal mechanical trigger that forces the mycelium to synthesize rich soil out of barren grit. After completing the cycle, we open the valve and slice the polymer hull apart. What falls out is a dense, dark loam, entirely unrecognizable from the pale sand we started with. This graphic compares the physical limits of the two materials. On the left, raw Sahara dust absorbs nothing, maintaining a 0% water retention rate. On the right, the newly engineered loam hits 80% retention immediately upon watering. To verify this is an active growing medium, we take seeds from pioneer species, hardy desert grasses and shrubs, and plant them directly into the extracted soil block. We subject these planted blocks to a simulated 2026 desert environment. We hit them with intense heat lamps and constant wind abrasion to ensure the soil holds its structure without crumbling back into dust. The roots grip the biological matrix tightly. We have manufactured an immediately viable agricultural medium capable of withstanding the planet's harshest climates. Because each unit costs just $9 in materials, the logistics for scaling are incredibly light. We can mass produce and bury millions of these individual reactors directly along the advancing global dust belt. This shifts the economic power back to local communities. Instead of relying on imported fertilizers, residents can actively convert barren wastelands into productive carbon sinks, generating their own fertile land. The blueprints for the hardware and the nutrient mix are entirely open source. Any independent bioengineer can download the protocols right now, source the recycled polymers, and start building reactors in their own region. We do not have to wait for large industrial firms to address soil sterility. Deploying this decentralized technology offers a practical method to stabilize local soil and secure food sources without relying on centralized industrial systems.